আমার প্রিয় ছাত্রছাত্রী, প্রিয় সহকর্মী এবং যে সকল দর্শক এই মুহূর্তে ফেসবুক লাইভ এবং ইউটিউব লাইভের মাধ্যমে আমাদের এই প্রোগ্রামটি দেখছেন, আপনাদের সকলকে আমাদের ফেসবুক পেজ এবং ইউটিউব চ্যানেলে স্বাগতম। আশা করি সকলে ভালো আছেন এবং সুস্থ আছেন। শুভ সন্ধ্যা সবাইকে। আমরা সবাই জানি যে আমরা একটা ক্রান্তিকাল পার করছি। আমরা বিশ্ব করোনা মহামারীর সময় আমাদের জীবনযাপন অতিবাহিত করছি। আপনারা ইতিমধ্যে অবগত হয়েছেন যে আমরা পদার্থবিজ্ঞান বিভাগ, পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয় এই করোনা মহামারীর সময়ে আমাদের ছাত্রছাত্রীদেরকে পড়াশোনার মধ্যে ধরে রাখা এবং পদার্থবিজ্ঞানের প্রতি ছাত্রছাত্রীদেরকে আকর্ষণ তৈরি করার জন্য আমরা ইন্টারন্যাশনাল ফিজিক্স ওয়েবিনারের আয়োজন করে যাচ্ছি এবং ইতিমধ্যে আমরা 105টা ইন্টারন্যাশনাল ফিজিক্স ওয়েবিনার সফলতার সহিত আয়োজন করতে সক্ষম হয়েছি এবং যেখানে আমরা বিশ্বের বিভিন্ন দেশের নামকরা পদার্থবিজ্ঞানীদেরকে আমাদের ওয়েবিনারে আলোচক হিসেবে আমরা পেয়েছি। তো এর পিছনে যারা আমাকে প্রত্যক্ষ এবং পরোক্ষভাবে সহযোগিতা করে যাচ্ছে তাদের সকলের প্রতি আমার কৃতজ্ঞতা এবং ধন্যবাদ জ্ঞাপন করছি আমি। আজকে আমি আমাদের ওয়েবিনারে যাকে আমরা স্পিকার হিসেবে পেয়েছি, আমাদের সকলের শ্রদ্ধেয় স্যার ডক্টর প্রশান্ত কুমার দত্ত স্যার। স্যারের প্রতি আমি কৃতজ্ঞ, কারণ আমাদের বিভাগের প্রথম বিদেশি যে আমি বলবো আলোচক ছিল ফেস টু ফেস আমরা যেটা করেছিলাম আমাদের একটা সেমিনার 2018 সালে, এবং স্যারের হাত দিয়েই আসলে আমরা ইন্টারন্যাশনাল একটা সেমিনারও সম্পন্ন করেছিলাম। তো তার জন্য আমরা কৃতজ্ঞ এবং স্যারকে আজকে আমাদের মাঝে পেয়ে আমরা সত্যিই আনন্দিত। স্যার শুভ সন্ধ্যা এবং আমাদের ওয়েবিনারে স্বাগতম।
শুভ সন্ধ্যা
এবং আপনাকে অনেক অনেক ধন্যবাদ এই ব্যস্ততার মধ্যেও আমাদেরকে সময় দিয়েছেন আমাদের ছাত্রছাত্রীদের কথা চিন্তা করে। যারা আমাদের ওয়েবিনারটা দেখেন, আপনারা ইতিমধ্যে জেনেছেন যে আমরা আমাদের ওয়েবিনারটাকে 3টা ভাগে ভাগ করি। প্রথমেই আমরা চেষ্টা করব আমাদের স্পিকার সম্পর্কে আপনাদেরকে একটু ধারণা দিতে, যদিও স্যারকে অনেকেই চেনেন। তারপরে স্যার তার বক্তব্য পেশ করবেন এবং শেষে আমরা একটা সময় রাখি, যে সময় যে কেউ চাইলে আমাদের সাথে সংযুক্ত হতে পারেন। আর আপনারা চাইলে ফেসবুক বা ইউটিউব কমেন্টের মাধ্যমে আমাদের স্যারকে আপনাদের প্রশ্ন করতে পারবেন। আমরা দেখে নেই আজকে আমাদের যে ওয়েবিনারটার টাইটেল অপটিক্যাল কোহারেন্স, এবং আমাদের স্পিকার ডক্টর প্রশান্ত কুমার দত্ত স্যার, প্রফেসর ডিপার্টমেন্ট অফ ফিজিক্স, ইন্ডিয়ান ইনস্টিটিউট অফ টেকনোলজি, আইআইটি খড়গপুর, ইন্ডিয়া। স্যার এখন প্রফেসর হিসেবে কর্মরত আছে, আমরা জানি প্রথম বিভাগ ইন্ডিয়ান ইনস্টিটিউট অফ টেকনোলজি খড়গপুরে, এবং স্যার তার ব্যাচেলার এবং মাস্টার্স ডিগ্রি ফিজিক্সে সম্পন্ন করেছে কলকাতা বিশ্ববিদ্যালয় থেকে, এবং তারপরে তার পিএইচডি ডিগ্রি সম্পন্ন করেছে ফিজিক্সে বর্ধমান ইউনিভার্সিটি থেকে, এবং সে কারেন্টলি interested in temporarily resolve the fast occurring phenomena in science such as carrier dynamics in semiconductor nanostructure, reaction dynamics in chemistry, phase transition in solid state media, and spin dynamics of magnetic materials. To achieve the objectives, different measurement setups like transient absorption spectroscopy, terahertz spectroscopy, magneto-optical Kerr effect, and nonlinear optical G-scan are developed in a newly built laboratory named Ultrafast Science Laboratory. আমরা তার ইন্টারেস্ট দেখতে পাচ্ছি লেজার ফিজিক্স, ননলিনিয়ার অপটিক্স, আল্ট্রাফাস্ট অপটিক্যাল স্পেকট্রোস্কোপি। আমরা তার পাবলিকেশনের কিছু অংশ দেখতে পাচ্ছি। স্যারের গুগল স্কলার আইডি সাইটেশন অলমোস্ট 1000 এবং রিসার্চ গেট আইডি তার 0.32.22। সো আপনাদের সকলকে ধন্যবাদ। এখন আমরা চলে যাব আমাদের স্পিকারের কাছে। স্যার, আপনাকে আবারও স্বাগতম আমাদের এ সময় দেওয়ার জন্য। এটা আপনার সময় স্যার, আপনি শুরু করতে পারেন।
Okay, thank you very much. First of all, I thank Professor Das for giving me this opportunity to deliver a talk. Actually, I interested to give talk for a series of talks for the undergraduate and postgraduate students. But this talk is basically a initiation for the initiation of undergraduate students in the field of optics. Okay, so let me share the full screen. Okay, just a minute. Okay, so title of my talk is optical coherence. All of you know this is a very important topic, and to enter into optics, first you have to learn what is coherence. This is very, and you know that in 2005, Professor Glover was awarded Nobel for quantum theory of optical coherence. But I am not going to discuss quantum theory of optical coherence. That we can do in a different another when we achieve more in this. When I cover some of the topics, then we can think of at the end that of quantum theory of optical coherence. Today, I will mainly concentrate on classical optical coherence. This is also called first order optical coherence, or maybe second order, up to second order optical coherence. Okay, so initially I will cover, so the contents of my talk is like this. First, random process. What is random process? What is stochastic processes? Then ensemble average and ergodicity. Then autocorrelation and cross-correlation functions. Elementary concepts of statistical optics. Then concept of temporal coherence, concept of spatial coherence. Then how this is used in actual devices like FTIR of Fourier transform infrared spectroscopy, then optical coherence tomography, then how to measure ultrashort pulse by intensity autocorrelation. So these I will cover, okay, in next 45 minutes. So initially, let us start with the uh, the propagation of a wave in free space. So all of you know it follows Maxwell's equation. From there, you can get a wave equation, and this wave equation del square E minus mu 0 epsilon 0 del 2 E del T square is equal to 0. This wave equation. Most basic type of solution is this one, a plane wave solution. ERT is equal to E0 cos k dot r minus omega t plus phi. Okay, so here you see that plane wave is identified with constant amplitude, and it has a constant propagation direction, one propagation direction k, and a single frequency omega. And you know that this type of solution is a deterministic solution. That means you can find out, you can predict what will happen, what will be the value of the function at some time or at some position. So that's why this is a deterministic function. So it is not a random function. So the plane wave solution is not the real world solution. It is an idealization. You will never get a light having this type of plane wave. The light either generation or in propagation. In generation process itself, it has a lot of randomness, because uh, there are cluster of atoms that generate the light. So different atoms, they have that generated light has different phase and their frequency. So that creates randomness. So the even if the light emits the atom emits light in 0 degree Kelvin, that also at this 0 degree Kelvin also there is Heisenberg uncertainty for transition from one level to another level. So that Heisenberg uncertainty, uh, that lifetime in upper level, that gives a broadening in the transition. So that is called lifetime broadening. So lifetime broadening introduces a band, frequency band in the radiation, and because of that there will be randomness. So every light, whatever light is there in real world, it is always a random light. Okay. So that's why this topic is important, that we can't generate a deterministic light. So light has always, say, particularly light that comes out of spontaneous emission, it has randomness. Even in laser light also, there is some randomness always. You cannot avoid randomness totally. So, so that here you see that uh, the just for the introductory students, that means first year students, for them, you know that this function, cost function, you see, it is a repetitive function, or you can see that you can define k by a wavelength which is 2 pi by lambda. Lambda is nothing but the distance for which that k dot r becomes 2 pi or in integral multiple of 2 pi, so that cost functions have the same value. So the minimum distance for propagation for which the oscillation, the cost function completes one oscillation, that is the length which we could define as wavelength. Similarly, frequency, we know that omega, this is a circular frequency, which is defined by 2 pi by lambda waveform. And this is, I just tell for the first year student, because that k has the unit of centimeter inverse or meter inverse, and omega has the unit of it is circular frequency, which is radian per second, or there is another frequency which is time inverse, we call it as hertz. Okay. So and if you put this solution, that e omega ert, okay, if you put this solution in the equation, then you get a relation which is k is equal to omega by c. This is called the dispersion relation. Okay, and you see for free space light propagation, this dispersion relation is linear. That means k versus omega, this curve is linear curve. Okay, and you get, using the Maxwell's equations, you get magnetic field amplitudes, and magnetic field also has the same in phase with the electric field. Okay, and usually we define electric field in complex, we take the help of complex notations. So when you introduce complex notations like E0 e to the power I omega t minus kz, then real part of it is your real electric field, and E0 tilde is given by E0 e to the power I phi. Okay, so this is a complex amplitude, and there is a phase here. So usually, most of the time, I will not put this real identifier. So when I write electric field like this, you have to assume that this is we are talking about the real electric field. So when light propagates in this way, the electric field and magnetic field, they oscillate in the two perpendicular plane. Okay. Uh, so uh, so this light, this is true for the entire range of electromagnetic spectrum, starting from radio waves to gamma rays. And you know that for the radiation up to microwave, you can measure the oscillations, number of oscillations. So tracing the phase is easier up to microwave, but when you go above microwave, then it is, the oscillation is so large that you cannot trace the oscillations. There is no detector which can trace the oscillation of this electric field in the visible or near infrared or in the ultraviolet region, because the number of oscillations per second goes to 10 to the power 12, 10 to the power 13, 10 to the power 14, 10 to the power 15, this type. So this cannot be traced by any detector. So so if you want to see how random is your radiation, this can be traced using by measuring the or seeing the oscillations in this range. Okay, the radio wave or microwave, but beyond this, it is not possible. So in this range, we have to see the randomness by different correlation methods. Okay, correlation, or maybe we can call it interference methods. Okay, so that is what. So for that, we have to first in this next slides, I will introduce some of the general term for the random functions, and then slowly I will introduce temporal coherence or spatial coherence of light. Okay. Okay, so random process is defined as if xt is an electric field or magnetic field vector of light beam, then xt is called a random process or random function of time if x does not depend on t in a deterministic way. Say cos function, sine function, or or x is equal to say t square. Okay, so in that case, you can find out in a determined way what will be the value of the function at some time. Okay, but there are many measurements that is not deterministic. Like say a, a, a voltage across a resistor. This is not deterministic. It fluctuates uh, in a very high frequency. Okay. Similarly, Brownian motions. This is also random motion. And then light emitted by spontaneous emission. This is also a random nature is there. You cannot predict about the electric field of the light for spontaneously emitted light. Okay. Now we define ensemble. Ensemble is for a set of possible realization or outcomes of a random function xt. The countable collection of all possible realization is known as ensemble. So all possible outcomes or measurements, this is called ensemble. Okay, a set is this set is called ensemble. Okay, then say like this, say we identify this that say for a duration of time 0 to t, I measure something and I repeat the measurement. And so 0 to t, you are measuring one by one and you are creating a function xt. Then when you repeat it, you identify with a identifier 1, 2 like this. So the ensemble average is the average over the number, that how many times you are measuring this. Okay, that 1, 2, 3, 4 like this. So ensemble average is defined xt. Average over ensemble is limit n tends to infinity 1 by n summation over r is equal to 1 to n xt r identifier. Okay, so this is the definition of the ensemble average. Okay, if pxt dx is the probability that, now this is just summation, I want to convert it into a integral. Okay, integral form. So in that case, I can define a probability. Say pxt dx is the probability that the random field variable takes the value over a range x and x plus dx. That means random field variable can take the value in between x and x plus dx at a time t, and for that the probability is pxt dx. Okay, so if if the uh, at time t, if there are n number of values that is coming within x and x plus dx, out of the total number of times that you have tried, then pxt can be defined as the n small n divided by capital N. Okay, where small n is the number that falls within this x and x plus dx, and n is the total number of trials. So this ratio is called the probability density. Okay, so where n is the number of times the value of x obtained within the range x and x plus dx out of the total n trials. Okay. Now, ensemble average we can define using in an integral form as integral x pxt dx. Okay, so this is the ensemble average. Okay, now time average of any typical realization of ensemble, time average is defined like this, that you are averaging over time. So that is limit t tends to 0, 1 by 2t minus t2 capital T xt dt r identifier. So this is r identifier is there. That means for a specific uh, 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 experiment, okay, specific experiment for a range of time. So you are taking the average over time. This is the time average. So time average, we will see that ultimately this, if for ergodicity, time average will be equal to the ensemble average. So before that, but that is true only for some specific type of randomness, that is statistically stationary. If the process is statistically stationary, then this two will be same. Okay. So ensemble average for product, if there may be two probability densities, say I define like this, that P2 x1 x2 T1 T2. This is actually second order, we can call it. So such that P2 x2 T x1 x2 T1 T2 dx1 dx2 represents probability that a variable x takes value between x1 plus dx1 at time t1 and between x2 and x2 plus dx2 at time t2. Okay, so ensemble average of product is defined like this. Ensemble average of xt1 xt2 is integral of x1 x2 p p2 x1 x2 t1 t2 dx1 dx2. Okay, for complex random function, zd is equal to xt plus iyt. This is defined similarly for second order, is z star t1 z t2 ensemble average is equal to integral z1 star z2 p2 d8 dz1 dz2, where dz1 is equal to dz is equal to dx dy. Okay, so what is statistically stationary process? I am just defining in these slides. I am just defining. So this is definitions which will be used in later slides. Okay, statistically stationary process or stationary random process. The random process whose properties do not depend on the origin of time or whose probability densities P1, P2, etc. remain invariant under translation of origin of time. Okay, that means you can take a difference of time in this case as a parameter because it does not depend on the origin of time. So here, so now I define this ergodicity. Ergodicity is defined as a statistically stationary process is said to be ergodic if the time average taken over the interval minus infinity to plus infinity of any deterministic signal, okay, signal of a typical realization, this one that we are measuring xt for many times we are measuring xt function. So for this type of the random process is equal to a corresponding ensemble average. So okay, so in this case, actually ensemble average is equal to the time average. So this type, then this is called this is the process is this statistically stationary process. This can be called ergodic. Okay. So for random processes, two parameters are important for finding the correlation uh, between different time or between different spatial positions. So these parameters are called uh, mean or average value and the autocorrelation. Okay, so mean value is defined as average of the uh, um, ensemble average of the parameter measurement values, and autocorrelation is defined as like this. Okay, x rt1 t2 is equal to xt1 xt2 average. Okay, so autocorrelation function, so this one is independent of time. So m, it should not be function of time, it is independent of time. Okay, but autocorrelation is a function of time. So that's why we take a time difference. T is equal to tau is equal to 2 minus t1. So we define r tau is equal to xt and xt plus tau. So this is the autocorrelation function, which is the average ensemble average of xt and xt plus tau. where RT is the measure of time over which there exists correlation between xt and xt plus tau. Okay, so this is the time for which, up to which there is a correlation between xt and xt plus tau. Okay. Okay. So cross correlation we can also define. This is actually second order correlation. Uh, Consider a situation where we require to measure the field variables at 2 points, say P1, P2. In such case, the process can be represented by using two random functions, x1t and x2t. Now assume that the process is jointly stationary. Jointly stationary means that the probability densities are independent of translation of origin. Okay, that for getting both x1 and x2, probability densities of x1 and x2 are independent of translation of origin of time. The measure of their correlation is called cross correlation, and mathematically this is expressed as R12 tau is equal to average over ensemble average over x1 star t x2 t plus tau. Okay. So in statistical optics, we define intensity. Okay, say your measurement electric fields. Okay, say this is URT is the electric field that you have measured at different times. So average of this, ensemble average of this, in okay, the intensity is defined as modulus of complex electric field square, and this intensity is instantaneous. That means it is depends on time. When a different time it will give you different value because of the randomness. Now if you take the average of these measurements, many times measurement values, that ensemble average, that will give you the intensity. Okay, then I can also define a statistically stationary process. For when the process is statistically stationary, that time average of the intensity, that is IR is equal to t tends to 0 1 by 2t minus t2 capital T modulus of URT square dt. Okay, so this is possible only for statistically stationary process. That means where it is independent of the origin of time. Okay, that means probability is probability of finding the occurrence, probability of getting the occurrence is independent of origin of the time. So for that type of processes, you can write it. So intensity, which is now independent of time, is given by this quantity, the average of this. Okay, so now let us enter into what is temporal coherence, what is spatial coherence. Okay, this can be many of you have already done experiments like say Michelson interferometer or Young's double slit experiment you have already done in your undergraduate. Okay, so I will use the same experiments to define or to measure the coherence. Okay, so temporal coherence we can define like correlation between the fields at different times. So this field at t E R T, another field is E R T plus tau. So how they are correlated between them. So this correlation gives you the temporal coherence. Okay, so for a deterministic wave, say plane wave. So there, if you measure at 2 times, and if you this measurement if you do many times, then you will see that your result is same. Okay? There is no difference in time for plane wave because that is a fully deterministic wave. But real world wave is not like that. So in that case, you will get completely different values at completely different values for these two fields at 2 times. Okay, if you measure many times. So that's why we'll define. So that will determine. So correlation, if you can, the way I define correlation, if we calculate the correlation between them, say self autocorrelation, then you can get a idea about temporal coherence, or you can quantitatively identify what is the temporal coherence of this source. Okay. Similarly, spatial coherence. This is calculation between fields at different spatial locations, say ERT and ER plus delta RT. Here also, for real light field, it is highly fluctuating. So for two positions, it will be, say in this case we didn't consider R was same. Okay, only one field is delayed with respect to others, that you can realize using Michelson interferometer. But in this case, these are at two different positions. So I take it like this, that this is Young's double slit experiment, where these are the two positions. At these two positions, you are finding out a correlation through interference. Any correlation you want to find out, you have to do with interference phenomenon. Okay, because the oscillation frequency for light is very high. That's why we have to use the interference method to find out the correlation. Okay. So interference is the measure of coherence. So interference with plane waves, it is very simple. You can, okay, we can define intensity like this. Intensity is proportional to the electric field squared, and quantitatively it is C epsilon 0 by 2 E0 star, where E0 is the amplitude of the electric field. So in Young's double slit experiment, if I use only plane waves, you see you can calculate the intensity. So superposition interference beams, this is one beam which is incident on the beam splitter. Part of the beam goes to this side, part of the beam goes to this side. You have two mirrors uh, which are in perpendicular directions, and after reflection from the mirrors, they superpose. After the reflection from the mirror, they superpose at this position. So one of the mirror, if I move, then you can control the delay between the beams. Okay, so this delay is given by this relation. Okay, here we have written that time delay. This is the time delayed electric field. So when they superpose, you get this relation. So I am calculating the intensity here after superposing the fields. So this is the superposed field, electric field. I am multiplying this with its conjugate. Okay, and multiplying this factor to calculate the intensity, C epsilon 0 by 2. So if you do the calculation, you see that you will have this multiplied by this. So that gives you E0 star. And again, when you multiply this with this, you get another E0 star. So that gives you together two E0 star. And another, this one multiplied by this. So that gives you E0 star cos omega t, because this one multiplied by this, so you are left with e to the power minus tau. Okay, omega tau. Okay, or plus omega tau here, e to the power I plus omega tau, because of multiplication of these two. And when you multiply this one with this, you are left with e to the power minus I omega tau. So these two together, that gives you 2 cos omega tau. So that's why you are getting an expression which is 2I0, because if you take common 2 here, then your I0 is E0 star multiplied by this, that gives you I0. And 2 if you take common, so 2I0 1 plus cos omega tau. So this function, if you can plot it, okay, you can plot with tau. So you will see that it has periodic values. So depending on as you move this mirror, you are continuously see maximum, minimum intensity here. Okay, so it is a highly deterministic uh, wave. That's why you can get maximum minimum like this. But it is not true when your light field is quasi monochromatic. So this is here we have taken perfectly monochromatic beam. Plane wave is a perfectly monochromatic beam. So that's why you got a deterministic interference pattern. But when you use a partially monochromatic, that means it has a central frequency. Along with it, it has some bandwidth of the beam. So when you introduce bandwidth in the beam, then your beam is no more plane. Your amplitude becomes function of time, and there will be phase because different frequency components they do not oscillate in phase, so they have different phase. So ultimately, a phase will come. So a quasi monochromatic, that means when it is not purely monochromatic, but it has a bandwidth of frequency which is much smaller than the central frequency. Okay, so in that case, your amplitude, which was constant in plane wave, it will not be a constant, it will be a function of time. And there will be a phase which is also not deterministic. The phase will be totally random phase, which will be a function of time, uh, not in a deterministic way. So in that case, so let us do that calculation. What happens for a, a, a waveform that we call when you have a bandwidth in a source in the light beam, we can define it as a waveform. Okay, it has some uh, say your amplitude becomes function of time. So intensity you can write as if it is a pulse light. Okay. So in that case, if you superpose these two, so what I am doing right now, I am doing the same experiment what I did with plane wave, and I got a intensity pattern like this, and I saw as I moved this mirror, I was getting continuously maximum, minimum like this. Now I am doing the same experiment by sending a light which is not plane wave, which is a light pulse. And pulse light is, pulse light is consist of many plane waves. Many plane wave, if you give a proper phase difference between them, then you can create a pulse light. Okay, or localization. A plane wave is a infinitely extended wave. It is continuous from in the propagation direction from one end of the universe to the other end of the universe, and also it is infinite in the transverse direction. Okay, so it is a but when you have many plane waves having uh, constant frequency separation between them, and a constant phase relationship between them, then you can have a localization of the wave in time. So that we call pulse. So pulse is nothing but a superposition of many plane waves, uh, the waves for which they have a constant frequency separation and a constant phase relationship. So if you superpose this type of plane waves, then you can create a localization of the amplitude in time. Okay, so that is what we call a pulse. So if I now send a pulse light for which frequency width is much smaller than the central frequency of propagation, central frequency of the wave, then we do the interference again and observe by moving this meter. So let us see what happens to the calculation. So this is the the electric field that is coming from one arm of the interferometer, Michelson interferometer, and this is another one with some delay. So now I calculate the intensity, and intensity will be defined like this: total electric field into multiplied by total electric field star into C into epsilon 0 divided by 2. This is the intensity. Okay, so if I do the calculation, we see that C epsilon 0 by 2, so we'll have many terms because this one multiplied by its conjugate. Okay, so when I multiply them, I get, you see, et star et e star t minus tau plus e t minus tau into e star t plus e t minus tau dot e star t minus tau, because there will be four terms like this. So this one we can call easily, this is intensity at t, this is intensity at this one also. Last term we can call it intensity at t minus tau. Because of the randomness, they will be intensity time dependent. Okay. Now this quantity in between these two, this is C epsilon 0 by 2 et dot e star t minus tau plus et minus tau dot e star t. This one, you see, this is nothing but conjugate of this, so that's why I can write it as real quantity. It will be twice of real, so that's why C epsilon 0 real of this quantity. Okay. Because just like this is a plus ib and this is a minus ib, so this will be summation will be 2a. So similarly, the real part of this 2 times of the real part of it. Okay, so we can now physical signal, that means if I send this light to a detector, so what detector will do? Detector cannot follow this much fast variation of intensity. Detector will average it out because its response time is limited. Say fastest photodiode has response time of nanosecond, but these fluctuations are faster than that. Okay, the very fast fluctuations. So that's why detector will see average value, and if we take the average, the integration, detector will integrate it. So I total t tau dt, if I do the integration from minus infinity to plus infinity, then we get these terms. Okay. So within the response time, it will integrate. So that integration we are getting these values. So first term is integration this one, second term integration is this one, third term integration is this one. Okay. So let us see what is this integration value. So this integration, you see, this is given by we can convert it into Fourier term. Okay, first we introduce a forward Fourier transform, and then we introduce a reverse Fourier transform. So that does not change. That means here, if I multiply with first forward Fourier transform and then again inverse Fourier transform, so you will get back the same function. So that is what I am doing. So here d tau e to the power I omega tau, I am multiplying integral 0 to infinity 1 by root over twice pi on this. And again I am multiplying a minus infinity plus infinity d omega e to the power minus I omega tau. So one is forward Fourier transform, then we are doing inverse Fourier transform. So that gives you, so this integration will give you the energy because you are taking the integration over time. So you will get this energy, or better you call it fluence. You will get fluence of this. And this one will also give you fluence. Okay. So now we can write this this quantity, this total signal quantity, that will be 2e. We take here this 2 term is giving you 2e, and here if I take 2e outside, then we have 1 upon e into this integration. Okay. real part of this quantity. Okay, so Fourier transform, first let me do some calculation. Say Fourier transform of this quantity. Say if you have a function h star t minus tau dt integral minus infinity plus infinity Fourier transform, that is nothing but that root over twice by modulus of spectral, and that means h omega mod square. So that is what I am writing here. H omega out of this. So that means here E omega. I am writing E omega mod square. So E omega mod square, if I multiply with this H nu epsilon 0 by 2, that is, I am calling it as intensity, spectral intensity, okay, or power spectrum, we call it I omega. So this is I omega. So you are left with, this is real part, and here 2 pi 1 2 pi goes away, root 2 pi. So 1 by epsilon, and 2 term, there will be a 2 here. So that 2 probably is coming from where? Okay. So this is the value. So the relation between this E star root over twice by E omega star, that gives you root over twice by 2 I omega by C epsilon. So this is the definition for the I omega. So that's why 2 is coming out of that. So 2 I omega is there. So that's why this 2 goes away. So 1 by E is coming inside. Okay, so this is the ultimate solution, that your total, if you that detector will see it like this. So signal detected by the detector is nothing but 2E 1 plus real part of, okay, gamma, I define it the coherence parameter gamma tau. Gamma tau is defined as this integration minus infinity plus infinity I omega e to the power minus I omega tau d omega integral. This E is nothing but this integration IT dt. So that's why, or maybe you can write it in frequencies, this is I omega d omega, because this quantity remains same. That is power spectrum and total integration, intensity integration over time, that is same. That is called Parseval's theorem. So that's why we convert it into in frequency minus infinity plus infinity I omega d omega. So this quantity is called the coherence, temporal coherence parameter. Okay, it can take a value from 0 to 1. So your signal that it will be detected by the detector is twice E into 1 plus real part of this gamma function, gamma term. Okay, so you can measure. So for a given uh, quasi monochromatic source, which is not deterministic, because of it has many frequency components, its amplitude fluctuates randomly. You can define a coherence. We can determine what is the coherence value of this source by with this values. Okay, so if you measure the intensities at different frequency and take the integration, okay, like this, then you can determine this quantity. Okay. Okay, now let us, I give you, actually I prepared it for the students. So if I give you a light field, which is like this, say maybe I is equal to I0 e to the power I e to the power minus t square by tau square, okay? Or maybe if I take a Fourier spectrum of this, temporal pulse is given by this, okay? Then, so this is the Fourier spectrum of a optical pulse, and this is given by t e0 r e to the power minus t square by omega minus omega 0 square divided by 2. If I send this type of optical pulse, so you see this is a Gaussian pulse. We are sending it into a Michelson interferometer. Now we want to calculate. So you see this is not a deterministic way because it has, okay, this is, we are not sending this one. This is one spectral component, but we are sending a pulse. That is, uh, actually I didn't write the pulse here. So pulse is e to the power minus t square, small t square by capital T square. Okay, so that is the Gaussian pulse we are sending. So so I am just showing you how to calculate the coherence parameter of this type of pulse, because this pulse is not a, when it is a pulse, the light will be random in nature because of the different frequencies. Okay. So here we calculate the quantities required to determine the gamma function. So first is this I r omega d omega integration. If you do this integration after putting this function here, using a standard integral like this, minus infinity to plus infinity to the power minus ax square plus bx plus c dx. So this gives you, this integration gives you root over pi by e to the power b square by 4a plus c. So with this value, you can put this function here and do the integration over uh, minus infinity plus infinity in frequency. So that gives you this quantity. Okay. So what we see now, we define the degree of coherence. So in the numerator you have integration minus t square omega minus omega 0 square e to the power minus I omega tau d omega, and in the numerator you have this quantity. Okay, so when I divide this, then ultimately you get t divided by root over pi minus infinity to plus infinity, this quantity. So this integration, again you can use this formula to calculate. Somehow you have to, this to, you have to put it in this form: ax square plus bx plus c minus ax square plus bx plus c. You can identify what should be a, b, c from here, and then do the integration again, and you get t by root pi root over pi by t square e to the power 2t square omega 0 minus I tau whole square. Okay, so what I see here, that we get back this gamma value with this value e to the power minus tau square by 4t square e to the power minus I omega 0 tau. Okay, so your signal is depend. So we know that signal is real part of this quantity. So real part is cos omega 0 tau. So this is 2e1 plus e to the power minus t square by 2t square cos omega 0 tau. So as tau is changed, and as you change the delay between the two pulses, two beams that is coming out of the two mirror, okay, in Michelson interferometer, as you change tau, then you can plot a function for this signal versus this tau. Tau divided by tau c. Tau c is a parameter I define based on the bandwidth of the frequency. Okay, so so if I plot t by tau c and corresponding this signal, then the function looks like this. Okay, so you see that the envelope is a Gaussian one. So this quantity determines the envelope, and cos omega 0 t is the oscillation function. Okay, this is the cos omega 0 t tau. Okay, so from the measurement of this, you can identify the coherence of this. So this gamma value gives you the coherence, how much, how coherent is the beam. Okay, coherent means the measurement of frequency bandwidth, that is the coherence. Okay, so if you get the frequency width of the beam, that will determine the coherence radiation. Okay. Now coherence time is determined like this. Coherence time tau c is integral minus infinity to plus infinity. This coherence parameter gamma tau squared d tau. So this is 2 into. So this function is, we have seen this can be given function, so we can write it as 2 into 0 to infinity mod value of gamma tau square d tau. Okay, and we define visibility. Visibility can be represented, okay, visibility is defined as maximum of the signal determined by the detector minus minimum of the signal. So this is maximum of the signal and this is the minimum of the signal. So this maximum minus minimum divided by maximum plus minimum. So this determines the gamma value. So this is equal to mod of the gamma. Okay. So so you can also try this, that find the fringe visibility and coherence time of a Gaussian pulse studied again. This for this Gaussian pulse. If I give you a Gaussian pulse like this, so you see this is a uh, uh, okay. So if you have a Gaussian pulse like this, for this you can calculate the visibility. Okay, this is a problem for you. You can calculate what is the coherence time of this type of this pulse. Okay, there is a problem. You can write it as ET, not gamma t. This will be ET. Okay. Actually, the ultimate gamma function will be like this. That's why we are writing the modulus of gamma is this one, and corresponding tau c the way I have defined. You can get root over 2 pi t. So okay, so this is all. You can try these problems. Now application of this uh, coherence, okay, temporal coherence, you can apply it to have a device, okay, that infrared Fourier transform spectroscopy. This is a very important device that utilizes this partially coherent light, okay, and determine the partial coherent light you can use as a source in a Michelson interferometer setup and measure the absorption spectrum of materials using this, okay, using this method, Fourier transform infrared spectroscopy. So all of you know that absorption spectrum you can directly measure using spectrophotometer, where two beam spectrophotometer you can use. So that is widely used in the visible region. Okay, but in the infrared region, that infrared spectrophotometer, if you use the same method, your resolution you cannot expect. You cannot get a very good, and also you cannot have a very good source in, that you can measure for the that particularly is the resolution is a problem. So, but you can use this interference method, that Fourier transform spectroscopy method, to measure the absorption spectrum of material in the hot infrared region. Okay, say from 2.5 micron to 25 micron, or maybe up to 50 micron. You can use this interference method. So what you have to do here, your source should have a very broad spectrum, maybe 2.5 to 25 micron, 2.5 micron to 25 micron. That is the bandwidth in your source, and you send this light through a Michelson interferometer. Okay, it is like this. Michelson interferometer. This is a broadband source in the infrared. It is sent through this beam splitter. One goes to this mirror, another 50% goes to another mirror, and after deflection they come and they form interference. So in the path of this interference, if I put a sample then the different frequency components will be absorbed in the material depending on the material's response property. So that will give a impression on the waveform that you get. Okay, so your waveform will have information about the material absorption properties. So if you take the Fourier transform of the waveform, then you can identify the different frequency components, how it is affected by the material. Okay, that what are the different frequencies that is absorbed, or whatever frequency component that is passed through the material. So that information, that transmission spectrum or absorption spectrum of the material, here you will get transmission spectrum. So you can get from the measurement of the Fourier transform of the waveform. So waveform I am talking about that this delay versus this interference that you are determining. Say here interference will be in a, so your detector has to be very pointed detector. You have put it at a very, as if it is a point source, point detector. So as you move this mirror, then for every position of the mirror, there is a delay between these two beams. Okay, delay between these two beams, and you get a interference maxima or minima depending on the value. Okay. Uh, Now, so I'm calling waveform means that tau versus this intensity pattern detected by the detector. That we call waveform. So waveform, actually this is the waveform. Okay. So, or better you call it a interferogram. We should not call it waveform. This is interferogram. So this interferogram, if you take the Fourier transform of this interferogram, then you get a spectra of this. Okay, that what are the different frequency components are there. So in FTIR, you measure the interferogram and take the Fourier transform. Interferogram data, you put it in your program, you write a code for the Fourier transform, and if you take the Fourier transform, then you get the different spectral components. Okay, so here we are doing the same thing. So signal is given by 2e. This is what detector detects, 2e plus 2 into real part of this quantity, that I spectral intensity into e to the power minus I omega tau d omega. So for different tau, you will get different value of the signal. Now for large tau, there will be no correlation, so gamma tau will be 0. Okay. So if I take a limit, tau tends to infinity signal tau, this is equal to 2 into e is equal to 2 into this quantity. That means there is no correlation. So there will be just background value. This is called background value, 2 into minus infinity plus infinity I t dt. Okay. So this quantity we defined like this, the energy, that is, or fluence. This is 2 into minus infinity plus infinity I t dt. So this will be your background, and given our measurement, we would like to find the power spectrum I omega. So Fourier transform of this signal that you have waveform, so that Fourier transform gives you this quantity. Okay, so Fourier transform of this quantity is defined like this. Okay, 2e, you see 2e 1 by root over twice pi minus infinity plus infinity. So this is delta function, and Fourier transform of this quantity, Fourier transform of 2 into real part of this. So real part, we can write it as sum of this and its conjugate. Okay. So Fourier transform of this is given by minus infinity plus infinity 1 by root over twice pi minus infinity. Just we put the expression for the Fourier transform, 1 by root over twice pi minus infinity plus infinity I omega prime e to the power minus I omega prime tau d omega prime. Then you put these values e to the power I omega tau. Okay, sorry, this should be minus I omega tau d. Okay, sorry, no, okay, this is fine. First you are putting the forward, okay, dt. Okay, actually this omega I have put a difference omega prime, and this is omega t. This is just for integration purpose. So similarly for this one also, you put the Fourier transform of this, and we are just exchanging this. So from here we see that uh, uh, if I take this integration of this quantity, okay, so if I take this d tau here and then multiply with this, so we get this expression. Similarly we do it here, and this quantity we can write as delta function of omega prime minus omega, and this is delta function of omega prime plus omega. Okay, so here you see the delta function we defined like this. Okay, e to the power minus infinity to plus infinity to the power I omega tau d tau. So this is delta omega. Similarly here, e to the minus infinity plus infinity to the power minus I omega prime minus omega tau d tau. So we can call it as delta omega prime minus omega. Similarly here, this will be delta omega prime plus omega. So these two quantities we are putting here, and you have integration over omega prime. Okay. So we are getting expression like this. So after you take the Fourier transform of your interprogram, you get this expression: root over twice pi minus infinity plus infinity I omega prime delta omega prime minus omega d omega prime plus integral minus infinity plus infinity I omega prime delta omega prime plus omega d omega prime. Okay, so this can be written. You see that this is nothing but this is, we can call it as if this is a summation of these two intensities at I omega and I minus omega. Okay, because okay, so first let me see that what will happen. This integration will give you two intensities, because this delta function will be 1 when omega prime is equal to omega. So directly you get this intensity as I omega, and here also I minus omega. Okay, when omega prime is equal to minus omega, then only this will be 1. So omega prime, here two things you are getting, two values. So one is root over twice pi I omega plus I minus omega. So we can now, you have taken the Fourier transform of the signal, that interprogram. If I divide with twice pi, then I am getting two things. Okay, earlier I got this expression 2 E0 delta omega plus I omega plus I minus omega. Now you plot it with frequency. So when omega is equal to 0, you have 2 omega. Okay, this is your background signal. Okay, this was already there. This is the incident intensity. So at omega is equal to omega 0 means that is incident frequency. You have this incident frequency, incident light field, central frequencies information. Okay, and apart from this, you have two more lines which is at a distance of omega 0, that frequency which is at a frequency of omega 0 and minus omega 0. So these two frequencies. So similarly, if you have a so this is the Fourier transform of the incident quasi monochromatic beam. after Fourier interference. Okay, so after Michelson interference of the quasi-monochromatic beam, you have got a Fourier, you have got a spectrum. So either you take this spectrum or this spectrum. Maybe this one is good enough. Okay, you take this spectrum. So if you put your material in the path of the interference, okay, here, if you put your material in the path of the interference, then material absorption signatures will be imprinted in the spectrum here, in the spectrum here. So you will see some of the frequencies are cut, absorbed. Okay, so this spectral band corresponds to the spectral component that was there in the source of the uh, in Michelson interferometer. So usually in FTIR, uh, the, mm, the the band is from 2.5 to 25 micron or like that. So within this band, the whatever material absorption signatures will be there, that you can find out from here. Okay, if you expand it, you can see there some of the frequencies are absorbed, some of the frequencies are passed through. So entire absorption signatures will be imprinted in this spectrum. Okay. Okay. So how much time I have? Pretam?
Sir? Okay,
How
so
much
you can
time I
carry
have?
another 10 to 15 minutes.
Okay. So I will finish by that time. Okay. So now let us see what is spatial coherence. So Michelson interferometer is a good experiment to measure the temporal coherence of a beam. Okay, that means coherence at or correlation at two times of a beam. Okay. Uh, Similarly, you can also measure transverse coherence. That means in a beam, if you want to see the correlation between 2 points in the beam wavefront. So in that case, we can use Young's double slit experiment. Say if I consider a source here, and from source we are away from this source, we have put a two slits which are at a distance r, and these two slits are equidistant from this Q point. And when the when the propagate here, they superpose on the screen, and you can get an interference pattern here. Now now we can verify what is the coherence between this or correlation between these 2 point sources Q1 and Q2. So this correlation can be measured by interference in Young's double slit interference. Okay, so we can write these two fields. This is U1 at Q1 and U2 at Q2 as this type of determines but very good wave, that is A1 cos omega phi 1t minus omega t. Okay, but okay, there is some time dependent. We are still considering that this is a partially monochromatic beam. So whenever you have partially monochromatic beam, your phase will be time dependent and amplitude will be time dependent. So that makes the beam that field non-deterministic. Okay. So similarly, this one is another electric field, that is A2 cos phi 2t minus omega t, where omega is the central frequency. Okay, mean frequency. And so after superposition, when they come and superpose here at some point on the screen, you have to take the superposition summation of these two fields. Okay, so these two fields is A1t cos phi 1t minus omega watt t plus A2t cos phi 2t minus omega t plus delta because of the path difference. So this delta is because of the path difference between these two. So we can calculate the intensity. Intensity you can make it, say here it is everything is real, so I take it U squared t, and when you do this you will have three terms. One is I1t plus, sorry, here it should be I2t. There should be I2T loss. So it should be I1T plus I2T plus I12T. There will be three terms. So when I calculate the intensity, making square of them. So this I1T is this one, I2T is this one, and I12T is this one. Okay. So here there is another mistake here. It should be minus delta. Okay, it should be minus delta. So you see that uh, if I now the detector will detect the average value, or we can call it, if I take the average or time average of this, then we get the values. You see that time average of this quantity is gives you half a square. Okay, if I consider that a1 is equal to a2, okay, if I take a1 is equal to a2, then you are getting half a square, and this quantity I want to average of this will give you, because this average uh, uh, okay, average of this will be, because of this term there will be average will be 0, so that's why we are left with average of this quantity only. So your interference, so this is the interference term. So this will be the background light, this two, I1T and I2T, this will be background, but this will be the interference term because it depends on time. Now, if the two partially coherent monochromatic beam, if I consider that their not phases are not dependent on time, okay, if I consider them perfectly, but it does not depend on time. In that case, there will be maxima minima depending on phi1 minus phi2 minus delta, if it is depending on the total phase, okay, that whether it will be maxima or minima. But there is maybe a situation that it is depends on time, but difference of this phase, if always it is constant. So this is called statistical similarity. This condition is called as statistical similarity. So to obtain interference, the interfering beams need not be monochromatic. So you see, if it is monochromatic, it is perfectly fine. In that case, these things will be G constant, I1, I2 constant. So no problem. So depending on the total phase, whether it will be maximum or minimum. So interference is there. But you can also get interference for partially coherent, that means partially monochromatic beam, where it is not perfectly monochromatic. If this phase difference at a always, phase difference is always constant, okay, at every time, it is constant. This is called statistical similarity. So if this is condition, then also you get a interference phenomena. Whenever interference is there, you can measure the coherence. Okay. So you can also define a mutual coherence function if you measure at 2 points. Okay, at Q1, Q2, and also at different time. So first function is U star R1T and another is U R2T plus tau. So, and if you, so to calculate the mutual coherence function, G R1 R2 tau is equal to this one, okay, average of this quantity, okay. And complex degree of coherence, this is actually those who work in coherence theory or optical coherence theory, they usually work with this. Actually, I am not going in details. So this is the function G R1 R2 tau, which is capital G. This is called the mutual coherence function divided by square root of IR1 IR2. Okay. Sorry. So, okay, let me go through some applications. So I give you one application is optical coherence tomography. This is widely used in medical field, uh, particularly for imaging of different physiological systems, physiological particular. You can, the advantage of this here, what, so first let me explain what is this. This is nothing but a Michelson interferometer. So here you have a low coherence light source. What is low coherence? That means it is partially coherent light, partially monochromatic light. It has uh, sufficient bandwidth. It has some bandwidth in the light. So it is a random light. Better we should call it a random light. Okay. So if you send this type of random light through this fiber, and this is a fiber coupler, so coupler will make this light 50-50 in two paths. So in this path, this light goes to sample, and in this path, light goes to a reference arm. So here, sample for sample, how to illuminate the sample with light. That optics is there, mirror, the lenses are there. So this lens collects the light from the fiber tip and makes it parallel, and then parallel light again falls on the another lens to focus it on the sample. Okay. And this from sample, the light will be reflected back and taken by this fiber, and again coupled by this coupler, so some light will be going to the detector. Similarly, from here also some reflected light will go to the detector. So here they will superpose. So interference will occur here, and this interference pattern will be measured by this detector. Now, whether there will be a constructive interference or destructive interference, that depends on what is the path difference between them. And path difference you can control by this reference arm. So if you move the reference arm continuously, you can get the maxima or the signal here. Okay. The advantage of this, that of this method, is that you can sectionally get a image of the sample. Say at different thickness you can get this image, because and uh, because the the thickness or the depth information is precise because of uh, the bandwidth of this light source. If you have more bandwidth, that means uh, that means more strict uh, thing. That means layer of the biological sample will be responsible for the interference pattern. Because for interference pattern, light will get a phase here. So that phase has to be uh, same with the phase here. So you are controlling the phase here. You are giving a restriction on this different layer. So you move this reference path accordingly. You get the image from different depths of the sample. So this is the powerfulness of optical coherence tomography. Now, to get a broader area, you have to move the sample. So first you take this position, then in XY raster scanning, you have to scan and completely take the image of it. So this is the your sample, biological sample, and this is the light path. This one, okay, this one is here. So you move the sample and get the image continuously. Say here, I have shown a picture of our finger tip. Okay, so you see when you take the image of the fingertip using optical coherence tomography, you can see the powerfulness of this. You see our sweat glands. Sweat glands are easily visible by this optical coherence tomography. So these are the sweat glands, and you see the tip of our finger has a lot of uh, inhomogeneity, or better you call it roughness. So that roughness is also visible from here, and sweat glands are visible by this optical coherence tomography. So this is a very powerful. So it's there are other methods for imaging in medical field, but optical coherence tomography is a very important one. You see, if you compare with them, say a magnetic resonance imaging or CT scan or ultrasound, or conventional optical coherence tomography, and optical confocal imaging. So if you compare them in terms of penetration depth, that much how much depth you can take the image, and their resolution. Resolution is also important. So optical uh, method, you see imaging resolution is very poor because resolution depends on wavelength of the light. Diffraction uh, ultimately limits the resolution. So for light it is 1 micron, and for OCT you are using the same light, so that's why resolution is same 1 micrometer. But advantage is OCT gives you a better depth. Here it is depth is up to, because there is lot of scattering in biological system. So optical imaging, optical method will not be useful. So that's why it has only 150 micrometer. That is the depth. But in OCT, optical coherence tomography, you can have a depth of 1 millimeter. In conventional OCT, okay, this is 10 micrometer. That is the resolution. Resolution goes down, but you can get the depth. Okay. In ultrasound, you see resolution is very poor, 150 micrometer, because you are using acoustic waves, and also depth is very high. So it is almost 10 centimeter. So this is used for USG, okay, for gallbladder or many diseases. Similarly, magnetic resonance imaging, it has 1 millimeter resolution, and but it has a large depth, okay, penetration depth. Okay, now I want to mention another application of autocorrelation. So this is very important. So this is the only slide where I have worked. Rest of the things I was presenting as a just from books. Okay, so this is the area where I have a setup in my lab. So if you have a very short ultra short light pulse, then how to measure its width? Because ultra-short light pulse cannot be traced in an oscilloscope. Because when you trace in an oscilloscope, you have to go through many amplifier, electronic amplifier, or maybe detector. The detector bandwidth is much smaller than the bandwidth of the light source. Or the usually detector bandwidth is in gigahertz, but your light pulse has a bandwidth of more than gigahertz. If you have a say a femtosecond pulse, so in that case it has a bandwidth of some terahertz bandwidth. So that bandwidth will not be supported by the oscilloscope, or maybe by the detector, optical detector, photodiodes. So in this case, you can measure the pulse width by using intensity autocorrelation. Okay, so I just describe how to do the intensity autocorrelation. So this is your pulse that is incident. We have to measure its temporal width. So pulse is incident here. You first split the pulse into two parts. One part goes to a variable delay, and another part goes to directly to the crystal. Okay, I will tell you what is this. So this pulse and this delayed pulse, they come also on a lens, and this lens focuses these two beams on a crystal, nonlinear optical crystal. So this is the frequency of this light is central frequency omega. Here also central frequency omega. But when they pass through this crystal, they generate second harmonic. This blue light is the second harmonic. Maybe this is red, this is red, but it is 2 omega frequency. That is blue light. So from red to blue light generation, and if you measure the blue light intensity for different delay, then you get a curve like this. Okay, so intensity measurement with delay of the because if this pulse, so what will happen as you change this delay change means you are moving this side. Moving this one means this beam is taking more time to reach here. So as if you are this pulse is tracing this pulse. This pulse is going over this pulse in the crystal, So when these two pulses are coinciding here, then second harmonic will be maximum. And when they are away from each other, as they go away from each other, their intensity, because second harmonic intensity is proportional to the multiplication of these two intensities. So that's why as the intensity goes down, say when this one maxima is falling tail here, then intensity will be going down. So when you slide one pulse over the other in the crystal, the second harmonic intensity go like this. So this is called intensity autocorrelation. So from here you can measure the temporal width of the pulse. So this is the FWHM 1.6 picosecond, and there is a factor to get back the pulse width, this pulse width. That factor, when you multiply, you get 2.3 picosecond. Oh, sorry, this is 2.3 picosecond, and from there you get 1.6 picosecond is the pulse width. Okay, 2.3 picosecond is this FWHM, and this is the actual pulse width. Now, if you take Fourier transform of this, you get the spectrum in frequency. So this gives you the bandwidth of how much frequency band is there in this light. So that also you can measure by Fourier transform. Okay. So just to mention that I didn't cover this theory of quantum theory of optical coherence. Professor Glover, Roy J. Glover, who was received Nobel Prize in 2005 for his theory, the quantum theory of optical coherence. And here they consider, say, I told you about first order, but you can also consider for 2n number of points. That is called nth order function. You can create nth order function by finding correlation in 2n different points in space and time. So this one we may discuss on another day. Today I am not covering this one. Okay, and I just want to mention that Professor E.C.G. Sudarshan, he was professor at TIFR Mumbai, and later on he went to University of Texas, and he gave the theory of quantum theory of optical coherence. But later on, Professor Glover was given a Nobel, but because of some reasons. But there was a controversy that whose contribution was how much. So if you are interested, you may go through the Wikipedia about this controversy, that whether that Nobel Award for quantum theory of optical coherence was whether Professor Sudarshan deserved it or it was given to the right person. You can read there. Okay. Okay, that's all for today. So I have covered, I have given an introduction to classical theory of optical coherence and its measurement, and I given the measurement methods, and few examples are solved. Then I have given effect of coherence in TIFR and FTIR, and optical coherence tomography is presented. Okay. Thank you. If you have questions, you may ask.
Thank you, sir, for your wonderful presentation. So if you allow that our discussion session, sir, we have got some question in our comment in Facebook, and we have got guest with us, so I can add our guest in our discussion, and I can read the question. So we have guest Dr. Kumar Shah and also Angon Chatterjee with us. So first question from Angon Chatterjee. So sir, how can
should I stop sharing?
Stop share. Yeah, you can stop share so that you can see the question and ask.
Just how to stop? Okay. Yes. Stop screen. Stop screen. Okay.
Okay.
Please.
So Angon, can you hear? You can ask directly.
Yeah. Good evening, sir.
Yeah. Good evening,
sir. Sir, I got a question for you. That how can a Bangladeshi student take admission into IIT?
Oh, in
What's
which
the
course?
procedure
For
In
which?
which
I
course?
for a graduation?
Bachelor,
Yeah, bachelor
bachelor
PhD,
course.
course.
PhD, bachelor.
Bachelor or
That
not?
you have to go through our national level JEE exam. Okay, national level JEE
So,
exam. So now it is held in many countries. In Bangladesh also, in Dhaka, you will find the center.
thank you, sir.
So JEE, you just give a search JEE mains. Okay, JEE mains, then JEE advanced.
Yes, sir.
Okay. Okay.
Thank you, sir.
Thank Hong Kong. So we have Shomiran Kumar Shah. So Shomiran, sir,
Yeah.
do you have any question?
No,
Thanks for
sir,
joining with us.
for your lectures, and also you delivered good lecture, and also this was helpful for us, and also I take this
This is not my topic actually.
so this is helpful for us, me. Thank you very much, and also we come to you to come our Department of Physics, Pabna University of Science and Technology, and thank you very much.
Thank you,
Yeah.
Shomiran, sir. So we have another question from Shubhat Shahu. Sir, how can we find the correlation between two single photon rays to two detector?
Actually, this is that I told that you have to take many measurements. Then only you can get a correlation. You just okay, one measurement. This is a very interesting question. That if I send one photon, whether it will go through the first slit or second slit. But this is not the case. Okay, that one photon experiment is very interesting. So this is always you have to take many measurements, then only you can get the interference pattern. So one photon, whether it will pass through first slit or second slit, this is a well discussed topic. Okay, that whether photon has any conscience to decide whether it will go through the first slit or second slit. If you read the book by Feynman has written that a day will come when people will find that photon has conscience to determine to go through selectively in one slit. Okay, but that is the case is that you have to take many measurements that then only you will get the interference pattern. Okay.
Thank you, sir. We have another question. So, sir, does the frequency of data matters in wavelength coherence?
Again, does the
So, does the frequency of data matter in wavelet coherence? So, I have added the question. You can see the screen.
where is it? Does the frequency of data in wavelet coherence? Frequency of data means in the in which one that in which measurement that FTIR measurement is talking about or any so here okay he can only write the question, he cannot join us, huh?
Okay, we can ask. So, Sarajan, you can join with us if you want to.
বাংলাতে question
হ্যাঁ, তুমি চাইলে বাংলাতেও কোশ্চেন করতে পারো। So we have another question from him. So is it possible to describe a light as sum of unpolarized and particularly polarized
this
light?
is yeah. This is a very interesting. Actually, I was going through a thesis that that coherence and polarization, they are related. Okay, there is a unified theory for polarization, coherence and polarization. Okay, that part I didn't cover here. Okay, so maybe what you probably you are asking that please remember today's topic is coherence. Okay, I have talked about coherence. Okay, polarization. We usually in your undergraduate course you will see that coherence is a one chapter that is related to interference, mainly interference. By interference you measure coherence, and you have a polarization another chapter at the end after diffraction. So you separately read these two topics, okay, polarization and coherence. But if you go, there is a theory, there is a unified theory of coherence and polarization. So here you are asking this question: is it possible to describe light as a sum of unpolarized and okay? Your ordinary light is definitely unpolarized, purely unpolarized. But if there is a part of polarized light within it, then we call it partially polarized light. Partially polarized light is if you have, say, some parts, maybe 30% light is perfectly polarized, say linear polarization, and rest of the 70% is totally unpolarized. So then this is called partially polarized light. So if you pass this type of partially polarized light through a polarizer, a linear polarizer, and if you rotate that linear polarizer, what you will see when that linear polarizer, output polarizer matches with your the linear part of the polarization direction, then you will have a very large intensity. That you will how much percentage will be passed through. Now there will be 30% already was there polarized, that part will be passed through, and out of 70%, another 35% will pass through. So you will have total 65% light passed through for a partially polarized light like this. Okay, is your answer clear to this?
Maybe so we have another question. We can sir, how time is negative in graph of intensity versus time graph?
Okay, so that is actually delay we are giving from. Oh, okay, in my slides, no?
Yeah.
Just I give it. Okay, just a minute. The delay we are defining like that. I show you. This is this one. Okay, so if this is the zero position of this mirror, then this side it is negative, this side is positive. We are defining time in this way. Tau is defined like this. For a given middle position is when this distance and this distance is same. That is the zero position. I call it two arm. When two arms are of same distance, then it is called zero position. Say here it is zero position. Now in this direction it is positive time. In this direction we call it negative. So this is delay. Positive delay, negative delay is possible. Okay, this is with respect to this light, how much time takes, and this light, how much time takes. So there may be sometimes it will be delayed. That means it will be positive. And sometimes it will be negative. Okay, with respect to this time. Is it clear?
Maybe, sir. Thank you. This may be the last question. So the beam splitter used in your experiment is 50:50 or others?
Yeah. 50-50, that will be give you better visibility. So usually 50-50 gives you the better visibility.
Okay, sir. So thank you. Thanks for your wonderful presentation and very good discussion session. So thanks again. So I have got one last question. If you allow, I can read the final question.
Sure.
Maybe the same person. I didn't get the point as the slide is not shared for. Oh, okay. So maybe when you answer his last question, maybe
Okay.
you haven't.
Oh, just a minute. Let me do that. Just a minute. Can you see this right now?
Yeah, we can.
So you see that that time is delay between these two mirrors. Okay, so this light takes time, and this light also takes time to get reflected. Now, when I put this path and this path same, then there is no delay between them. They will come simultaneously. Now, if I move this mirror a little bit this side, then this light will take more time to reach here. This light will take less time. So there will be positive delay. So tau is positive. Now, if this mirror is moved this side, then this light will take less time. This light will take more time. So in that case, delay will be negative. So this is how tau is getting negative or positive. Okay.
So thank you, sir. So I think students have learned a lot of things about the optical coherence. So we are very grateful to you that you have given us time.
Actually,
in this corner.
I somehow, I didn't prepare anything. Okay, this was just I take a class. I had many slides, so I
Great,
took
sir.
some of them and presented. But
So,
okay, this is just this talk is
Beginning.
for initiation of the students, for maybe undergraduate students in optics area. First, you have to know what is coherence. Otherwise, you cannot enter in optics area. Okay, so maybe later on I can talk about my area. Okay,
Okay,
talk
so
on
thank you. That will be very
laser physics or nonlinear optics or ultrafast science that I can present. Okay.
Yes, sir. Thank you, sir. And
Okay.
we'll arrange another webinar very soon with you in your related field. So thanks again, sir.
In my field, I have better slides. Okay.
Yeah.
With
Okay,
colored things and everything. Okay. These slides are just like class notes. Okay.
Okay, sir. So thank you.
Thank you.
Bye for
Thank you
today,
very
sir.
much.
See you very soon,
Bye.
sir.
Bye. Bye. Bye.
Namaskar.